Am I audible, Sagar?
Yes, sir.
In- Hello?
Yes, sir.
Is the screen visible?
Sir, your voice is like a lot of loudness.
Okay. I am asking whether the screen is visible or not.
Yeah, screen is visible.
Okay. So perhaps we'll wait for some time till other people join. Then we begin. Hmm. I think other people are not going to join. Uh, Let me start because there are certain things that need to be covered. So, hello everyone, and this is the first time we are going live on YouTube. So, hello everyone, all of those who are watching on YouTube as well. And I am Aniruddha, PhD scholar at IIT Indore. And today we'll be looking at the big three contexts that are countably additive set functions on intervals and the uniqueness problem for measure. So, what all things we saw was that given a countably additive set function, we can find the monotone increasing function, which is right continuous in this manner. So, suppose we have a countably additive set function from the set of all left open, right closed intervals to 0 infinity. This is countably additive. Then we can define this f from R to R. How do we define it? F of x is mu of 0 to x when x is positive. It is 0 when x is 0 and minus mu of x to 0 when x is negative. So we verified that this is a monotone increasing and right continuous function. Okay. And one thing we observed was that to prove monoton increasing, only finite additivity was sufficient. Finite additivity is sufficient. And one of the questions that was left was that suppose you are given a monotone increasing right continuous function, whether we can say that it comes from a countably additive set. So, Kupusamin, do you have any question?
Sir, good evening, sir.
Good evening, good evening.
I have one doubt, sir. In the weekly assignment of 3,
Okay.
sir, the doubt is, sir, diagonal number. So,
Uh,
the weekly assignment, the questions, they ask only the set of diagonal numbers.
right, right.
So, we can add one irrational number with the diagonal number. So, what is
Uh,
happened, sir? Irrational number or a diagonal number?
no, I couldn't understand it. If we added irrational number to a dyadic number, then what happens?
Yes, sir.
No. What is the question?
So, so question is the set of all diagonal numbers, sir.
Uh-huh.
So question is the set of all diagonal numbers, sir.
Yes, go on. What about that set?
Suppose I can add one irrational number with the diagonal number. So
Uh-huh.
what happens, sir?
What happens in what sense?
What is mean? That is the irrational number or diagonal number collections. That is
Uh,
my doubt, sir.
okay, so you are adding a dyadic number, so it is of the form 2m by 2 to the power n, right? Where m and n are integers.
Yes,
Is
sir.
that
Yes,
right?
sir.
Okay. You add one more, like you add a irrational number here.
M and belongs
So,
to this is the rational number format, sir.
correct.
But
So this
here
is what you are
asking
asking,
one
right?
question, sir.
Uh-huh.
Uh,
So say this is a number, okay. What do you
some
want to
element, so you take some element that belongs to the irrational number. Suppose the R belongs to the irrational number. So we can add M divided by 2M plus R. This number is irrational or diagonal number, sir.
say a rational plus an irrational has
The
to be an
form
irrational number, right?
irrational.
This, yeah, suppose this is dyadic. If this is
Yes, sir.
dyadic, then it is rational.
Not rational.
Okay. Dyadic numbers are rational numbers.
Yes, sir.
So, but once this is rational, then R becomes rational. So this cannot be dyadic.
Yes, sir. Yes. My doubt is this is one. So another one doubt, sir.
Uh-huh.
So in the interval, the boundary points are irrational number.
Okay.
In the interval, the boundary points are irrational number. This collections is sigma algebra, sir.
Only irrational number.
Yes, sir. Bound points are in irrational numbers.
Then that may not be a sigma algebra, right?
Okay, sir.
See, for okay, can you think why it is not a sigma algebra? So let us write it. Suppose I consider this S as the collection of all intervals I, such that I is an interval and
Okay, sir.
endpoints are irrational.
Irrational.
Okay, so can you think why this is not a sigma algebra? See, okay, for this to be sigma algebra, what all need things you need to check?
So empty and whole set belongs to the collection.
Right. So is the whole set inside this? Your voice I am not able to hear. So what do you think? Is the whole R inside S?
Hello.
Tell me, tell me.
Problem.
Okay, can you hear me?
It's a small network problem, sir.
No issues. So what I am asking is whether all of R is inside this S.
I cannot. I
See,
don't.
does R have any endpoints?
Boundary points are irrational, sir.
That is fine. So this is the
No
collection
end.
of all those intervals whose boundary points are irrational. But does the set R, the
Yes,
set of real
sir.
numbers, does it have boundary points?
Sir.
Okay, did you understand my question? What I am asking?
No, sir. No, sir. No, sir. No, sir. I
Okay,
cannot understand, sir.
okay. See, we have found this collection, right? You said that let us collect all those intervals whose endpoints are irrational numbers. Is
Yes,
this
sir.
what you want to form? Okay.
Oh, okay, sir.
So I am asking you, what are the endpoints of real line?
No end points, sir. Real lines.
So does R belong to S?
No, sir.
No, right? Because it doesn't have any boundary points. So this cannot be a sigma algebra.
Okay, sir. Okay, sir. Thank you,
Okay,
sir.
now what we'll do, let us move one step ahead. So see, this is the problem because R doesn't have boundary points. Let us add R separately. So union with R. Now do you think this is going to be a sigma algebra?
Sir. Again, sir. Again, one time, sir.
Yeah. So what I am saying is, see the earlier construction was not a sigma algebra because by definition, the set of real numbers was not inside S. Is that fine?
Yes, sir.
Okay. So what I do is I purposefully add that set of real numbers inside S. So let us take all the intervals whose endpoints are irrational and let us take R also inside S. Now does S form
Okay.
sigma algebra? So again the question is S and sigma algebra?
Okay, okay.
So what do you think?
Yes, sir. Sigma algebra.
Are you sure? Why is it a sigma algebra? Again let us see what all things we have to compute.
So boundary points also included, sir.
Yeah, that is okay. But see, for sigma algebra, what we require? Empty set and R should be like empty set and the whole set should be inside S.
Empty set and
Complement
whole
should
set
be inside
belongs
S.
to complement and set. You take any set that complement belongs to the same the collections.
Correct. So you take an interval. What
Uh,
is its complement?
complement
So you take suppose this interval, doesn't matter whether it has irrational endpoints or not, its complement is going to be union of two intervals, right?
Yes, sir.
This is no longer an interval. So complements are still not
Yes.
inside us. So this is still not a sigma algebra,
Oh, okay, sir. Okay, sir.
right? So
Yes, sir.
and even if you purposefully like add complements also, then there is going to be a problem of countable unions because you can always
Okay.
find. Uh, so do you know what is meant by density of rationals and irrationals in R?
So density,
Yes, density of rationals and irrationals in R. Do you know what this means?
so measure value.
But we have not studied measure, right? This is something from basic real analysis. See, what it says is that given any two real numbers, given A not equal to B, suppose that A is less than B, because if B is less than A, we can do the opposite thing. You can find a rational number and an irrational number such that A is strictly less than or strictly less than B, and A is strictly less than Q, strictly less than P. So, using this, one can prove. So, okay, I will leave it to you perhaps. You just check this that there is a sequence of irrationals that converge to zero. Okay. So, okay,
Okay, sir.
can you give me some idea how are you going to prove this using whatever statement I have written above?
Sequence of operation. So I don't know, sir.
Okay. So, see, let us start. What I want for every natural number, I want to extract an irrational, and that irrational should be of the form that slowly goes towards zero. So, how will I do that? Let us see. So, zero is not equal to one, right? Do you agree on this?
Okay.
Right. So, there is an irrational. There is an irrational number between 0 and 1. Is that right? So let us call it R1.
Okay, sir.
Okay. Now, 0 is also not equal to half. In fact, I should write 0 is strictly less than 1 and 0 is strictly less than half. So there is
Okay,
a
sir.
R2 in irrationals between 0 and half, right? Yeah. Do you agree with this?
Yes, sir.
Okay. So if I continue doing this, basically what I am saying is for every n, we can find an irrational number Rn which lies between 0 and 1 by n. Okay. From here, can you say that
Okay.
Rn converges to 0?
Yes, sir. The limit n tends to infinity. We get the
Correct.
sequence.
Okay. Because 0 is a constant sequence, 1 by n converges to 0. So you can take
Yes, sir.
sandwich lemma. Sandwich lemma tells us that the in between sequence must converge to 0. So limit Rn
Yes, sir.
converges to 0. Now let us consider this collection of sets. Consider In as Rn comma root 2. So is this collection, I mean, is this In inside our S? Can I say this?
Yes, sir.
Yes, right? Because the endpoints are irrational. Now,
Yes, sir.
what about the union of INs? Infinity Rn comma root 2. So what do you think this is going to be equal to? So see, let us make a diagram. So somewhere here is 0, here is root 2, here is 1. My first R1 was here, right? It was between 0 and 1. My R2 may be somewhere here, right? Or, okay, in fact, what I can do, construction I can change a little. So R2 I can make between 0 and R1. And similarly, Rn I can make between uh, Rn minus 1. Did it work? Correct. Okay, let us keep that original construction. No worries. Half and then 1 by n. Okay, so somewhere here was R2. Maybe R3 is here. R4 is here. But what happens is after a certain time, Rn comes very close to 0, right?
Yes, sir.
So what will happen? Hmm. So, okay, again, you can check it. Check the fact that for every x positive, you can always find some n such that Rn is strictly less than x. And this simply happens due to the Archimedes equation. So, okay, now with this observation, now can you tell me what is this union? Union of Rn comma root 2? I couldn't really
So
understand. Do you repeat?
0 comma root 2.
Correct. So this is 0 comma root 2, right? And
Yes,
why
sir.
is this so? Because negative numbers cannot be there. Because no
So,
negative number is inside any of this interval. This is always like the positive thing. Numbers bigger than root 2 cannot be there because again they are not in any of these intervals. And due to this claim that I have made, and one can easily check this claim, every positive number between 0 and root 2 is inside at least one of these intervals. So this is exactly equal to 0 root 2. Now, is this inside our S?
boundaries are irrational numbers. Are
So is this inside S?
so it's not yes.
It is not in S, right?
Yes, sir. Does not
Because the
belongs to
boundary,
yes.
right? Because the boundary is now like one of the boundaries is rational.
One of the boundary is not irrational.
Correct, correct. So do you understand the problem with this collection? It does not satisfy really
Yes.
anything. Neither the
Yes.
complements are
Yes.
here nor the countable unions are here.
Yes, sir.
Any other question?
No, thank you.
What about there is one more participant, Prasad?
Yes, sir. I have a doubt in assignment.
Uh-huh.
So can I share the screen?
See if you don't know whether you can or not. Are you allowed to share the screen?
Okay, sir.
No, no. I mean, are you getting the option to share the screen? Then you share it. No issues.
Okay.
Yeah, so I have allowed you to share the screen. Now you can share it.
Sir, is my screen is
Yes,
visible?
yes, yes. It is visible.
Okay. Sir, are you
Uh-huh.
sir in example number 8 and 9 in problem number 8 and 9?
Uh-huh.
So what is the difference in these two problems? I didn't get it. Because sir, if the if the sequence is increasing, then certainly it would be either divergent or it will be convergent.
right? So either it will convert to
What is the
finite point or it
difference
will.
between these two questions, sir? If one has, what is the difference, sir? In
So
example number 9, the limit supremum n tends to infinity of mu n, then certainly it would be either convergent or divergent.
correct. It is an
So
increasing
it
sequence.
should be
Right?
same as example number 8.
Hmm. Right. Right. It is same as example.
So I have a bit confusion in it. So I
No,
didn't
no.
get.
Yeah. So whatever answer for it, the same answer should be for 9 as well.
Yes, sir.
Because in this case, lim sup and limit are same.
So, so if there is
So
some mistake, you can take the note, and if there is some any other concept, you will explain me later on, sir. But I am asking that.
no, actually, yeah, we'll have to notify NPTEL team that there might be some error in question 8 and 9.
Yes, sir.
And so, do you want me to explain what is the difference between limit and lim sup?
I I have marked the example number 9. Uh, According to example number 8, I understood example number 8 how it become a measure. So
Okay.
by that same concept, it the answer of the 9 should also be true, sir. It also should be a measure.
Yes, yes, I agree with you.
Yeah.
Yeah. So, if only that is the issue, then we'll notify the NPTEL team.
Yes, sir.
If you
Thank.
have any conceptual question, then you ask me.
Okay, sir. So in example number 3, so the answer is one and only one. I I understood two implies one, but I didn't get one implies two.
What is what is you take any collection whose union is there, and then this happens. Yeah. So, okay, this also may not be correct because we have not given that mu is finitely additive, right? If mu
Yes,
were finitely additive, then one implies two would hold. Otherwise, it.
yes, sir. Yes, sir. Sir. So these two
Okay.
problems
Let me.
I face.
Uh, this is which assignment?
So it is assignment number 2.
Assignment number two.
Yes, sir.
Okay, just wait. Assignment two. What are the problems? Problem number
So
three
problem
and
number 3
eight nine, right?
and and other was 8 and 9.
Okay. Okay. So I have noted it down.
Okay, sir. Okay, sir. Thank you, sir.
Okay. Anything else? Can you stop sharing so that I can share the screen again? Thank you. Yeah. So is my screen visible now? Can someone just tell me is the screen visible now?
Yes, sir.
Yes, sir.
Okay. Okay. So right. What were we going to do? Okay. Before we do anything else, let us go to one thing that was left in class as an exercise. I want to know whether you people have tried it or not. So we saw one of the results that said that characterized countable additivity whenever the set function was totally finite, right? So we saw this result. The result was that if A is an algebra and mu from A to 0 infinity, this is a finitely additive set function. Finitely additive set function. Then mu is countably additive if and only if for any sequence an in A with the property that an is decreasing, decreasing, right? So an contains an plus 1. We have a measure of intersections of ans. This is equal to limit measure of ans. Yes, for finite set function, and there was this assumption that mu of the whole set is finite. Okay. So this was the conclusion, and then the question was, what happens if mu x is infinite? So have you people tried it? What do you think? What happens? Can we conclude this same thing? Yeah, Kukusan, are you there?
Yes, sir.
What do you think? Suppose that measure, I mean, mu of x is plus infinity. It is not finite. Then does this conclusion? So the question is, if mu x is plus infinity and mu is countably additive, can we say that measure of intersection of ans is equal to limit measure of ans whenever an is a decreasing sequence? So tell me, what are your thoughts on this? So if there are any YouTube audience, they can tell me through the live chat. Okay, so okay, in this Google Meet audience, at least you respond. So Prasandeep, are you here?
Yes, sir.
So what do you think? Can we really say this thing that this happens?
So I'm thinking, so just a minute.
Oh, okay. And what about Kusami?
I know no idea.
Did you not attend the lectures? Okay, no problem. So let me give you a hint. What happens if we take the algebra of all intervals, the algebra generated by all intervals, and then let us look at the length function. Consider A as the algebra generated by intervals and the length function. So what do I mean by this? So algebra can have unions of these intervals, right? So lambda of a disjoint union of intervals j from 1 to n is just this summation lambda ij. So by definition, it is finitely additive. Finitely additive. And in fact, one can check also countably additive. We have already sort of seen this in one of the lectures previously. But yeah, to convince yourself, you can check that this is actually countably additive. Now, see with this thing, what is length of the whole real line? Yeah, can one of you tell me?
Zero.
No, no, length of whole real line. How will it be zero? See, the length is plus infinity,
Infinite.
right? It is plus
Infinite.
infinity. Yes, correct. And let us now consider this particular collection. Let us consider AN as closed interval n to infinity. So the question is whether AN is decreasing. That means, can we say that AN contains AN plus 1? So what do you think? Yeah, Prasanji?
Yes, sir. Decreases.
Yes,
Yes.
it is decreasing, right? This is indeed a decreasing. And what is its intersection? So, okay, to understand this, let us again draw a figure. This is 0 and this goes to plus infinity. 1, 2, 3 and so on till n. What I'm doing? The first interval is this, starts from here, goes towards right. Second one starts from here, third one starts from here and so on. So, what can you say? What is the intersection?
Empty, sir.
Empty, right?
Empty.
Why do you think it is empty?
The interval n comma n. That means infinity comma. So,
No,
so.
no.
No, no.
That is not the correct way. You cannot estimate something from here.
Closed
See,
interval
this
one.
is this is empty. Yes, Prasanji. Yes, Prasanji.
So closed interval 1 comma 2.
Closed interval 2. Are you saying this?
No sir, no sir. Sorry. Sorry sir.
So see, okay. So when will we say that this intersection is non-empty? So intersection n equal to 1 to infinity, n comma infinity is non-empty. This is same as saying there is some real number inside this intersection, right? But if this happens, this means there is a real number such that for every n, this x is bigger than or equal to n. Is that right? Yes. Is whatever I am writing, is it correct? Okay, Prasandeep, can you tell me, is this correct or not?
Yes, sir. Yes, sir. Uh,
Yes, Prasandeep. I really could not understand what you said, so please repeat.
Yes sir.
You agree, right? That this is true. But what does this mean? It means that the set of natural numbers is bounded in R. And this is a contradiction to the Archimedean property. Therefore, it cannot be empty. Something which is not non-empty is okay. So this intersection is empty. So what can you say about the mu of, or rather the length of this intersection? So the length of intersection AN is length of the empty set. And what is the length of empty set?
0.
0. On the other hand, what is the length of each AN? That means length of each of these intervals, n to infinity.
Sir, infinite.
Infinite, right? This length is infinite.
Yes.
So what about this limit of these lengths? Yes.
Infinite.
Infinite, right? Because it is a constant sequence. This is plus infinite. But this is not equal to 0. So you see the problem, what happens? If something, the whole space has infinite length, then we can always find the subsets of infinite length whose intersection is empty, but then this equality cannot hold. That limit lambda an is not equal to lambda of intersection a. Is this clear? Yes, no. Tell me, is this clear or not? I couldn't understand this one.
Yes, sir. I understood.
So okay, so this was one of the problems. So this result is not true if mu of x is plus infinity. It is only true when mu of x is finite. Okay, another thing was there was a exercise to prove the following. It said that suppose again mu from an algebra to 0 infinity is a finitely additive set function. Sorry. Is a finitely additive set function such that mu of x is finite. And then we have to prove that mu is countably additive if and only if for any sequence an in A which is decreasing and the intersection is empty, what we have is this limit of mu ak mu ans is 0. So right. So how do we prove this again? Any ideas in proving this? See, okay, let us go one by one. So it is a if and only if statement. So assume that mu is countably additive. We want to prove the other conclusion. Is that conclusion easy? Yeah. So Upulsami, are you here?
Yes, sir.
What do you think? Is this conclusion easy to prove? Suppose that mu is countably additive. then we have to prove this, that for any sequence an which is decreasing and its intersection is empty, limit of mu an is 0. See, let us look at the previous result. What it said what? That mu of x is finite, then mu is countably additive if and only if for any sequence which is decreasing, we have the measure of intersection an is limit of the measure of an. So here this intersection an is empty, right? So from the previous result, measure of intersection of ans, this is limit of measure of ans. Well, I should not say measure because, well, they are calling it a set function for the time being. But anyway, on the other hand, this is what? This is mu of the empty set. But since this is a totally finite set function, the mu of empty set is 0. So limit of mu ans is 0. Is this fine?
Yes, sir.
Okay. What about the other way around? So other way around means it is given to us, given that whenever an is a decreasing sequence, that means an contains an plus 1 and intersection an is empty, we have limit mu an is 0. And we want to prove that mu is countably additive. So let me ask you that is it sufficient to prove that if an is a decreasing sequence and not necessarily intersection is empty, then mu of this intersection is equal to limit of mu of ans. So what do you think? Is this sufficient? Yes. Prasandeep, do you think that is this one is sufficient to prove what we want to prove?
So we have to prove countably additive, and
Correct.
and in countably additive, the union of countable union, the pairwise there should be pairwise, mutual pairwise.
Right, right.
This,
So that is a definition of countable additivity.
yes,
But
sir.
we have seen this result, right? See, the previous result said that whenever mu of x is finite, whether you say mu is countably additive or whether you say that mu has this particular property, that those two things are same, isn't it?
Yes, sir. Then by this theorem, it is
Right.
sufficient
So it
to
is
prove that.
sufficient to prove that whenever we have a decreasing sequence, mu of intersection an is limit of mu of an. Okay, so let us start. What we want to do is we want to look at mu of intersection ans, but all we know is that whenever intersection an is empty, limit mu an is 0. So since we have a decreasing sequence, let us take a decreasing sequence. Suppose this is my A1, then we have A2, then we have A3, and so on. And perhaps this is the final intersection A. And somewhere in between we have AN. Let A equal to intersection of ANs. So what we want to do is we want to construct a sequence. Say let us call it Bn, such that Bn is decreasing and intersection of Bn's, this is empty. Can we do that using this sequence An and the intersection? What do you think? Yes. Anyone? Kupusami?
So B1 equal to A1, B2 equal to A2 minus B1,
Okay, wait. B1 equal to A1, B2 equal to
A2 minus B1.
A2 minus B1. See,
Oh,
A2
no, no,
minus
no.
B1 is, wait. See, A2 minus B1 is collection of all elements which are in A2 but not in B1. Is that possible? This is going to be empty, right? Yeah, Kupusami?
No, sir, no, sir. Something,
It
sir.
is empty, right? So, see, ultimately what we want is that intersection should be empty. So, let us do one thing. Let us define it like B1 is A1 difference A. So, that means I am collecting these, all these from here to everything outside. This is my B1. Next, what? I want a decreasing sequence. So, I have to reduce the size. What can I do now? Let us consider B2 as A2 in difference A. So A2 difference is all of this thing. This color is not good. Maybe this color is good. All of this thing. And then so on. So in general, Bn let us define A and difference A. So the first question is whether Bn is decreasing. What do you think? Does this construction tell us that Bn is a decreasing sequence?
Yes, sir.
Yes, right? Because An itself is a decreasing sequence, and we are, basically removing the same set every time. It still remains a decreasing sequence. So this is yes. Yes, it is. Now, what is the intersection of Bn's? Can you tell me what is it? Perhaps Prasanjit can tell me what this intersection is.
So can you please show the diagram?
Yeah. Is it visible? Okay. So now tell me what what is this intersection? Maybe let me just mark one more set, then perhaps it will be clear. So A3, right? So A3 is still small. Okay, can you just expand A and difference A for me? Yes, still.
Yes, I think it is tends to 5.
Empty, right? Why?
Yes,
Let us try to write the definition. So this is intersection of n from 1 to infinity, A and intersection A complement. But intersections have a nice property of associativity. So I can write this as intersection n from 1 to infinity A n intersection with A complement. But this is A intersection A complement, which is empty, right? Do you agree?
yes, sir.
Okay. So now once this is empty, my assumption, so it is given to us that whenever we have a decreasing sequence whose intersection is empty, limit of mu A n is 0. My assumption, limit n going to infinity, mu Bn is 0. So that means what? What is Bn? Bn is A and difference A. But what is mu of A and difference A? Yes. See, remember that mu is finitely additive and the mu of whole set is finite. This is what we are going to use. So just by this, can I write this as mu an minus mu a? Can I go from this step to this step without a problem? Yes. Yeah. Ukusargi?
So no idea, sir.
See. Okay. Let us take a little digression and let us try to prove some. So I claim that if mu from any collection to 0 infinity is a finitely additive set function and for A, B, and C we have A subset of B and B difference A is also in C, then mu of B difference A, this is equal to mu B minus mu A whenever mu B is finite.
Yes, sir.
Have we seen this? Have we seen this type of a result in the class?
Yes, sir. Yes, sir. Yes, sir.
Yeah. So how do you prove it? You simply write B as A union B difference A. Proof is you write B as A union B difference A. This is a disjoint union. Therefore, mu B is mu A plus mu of B difference A. And since finitely additive set functions are monotone, this is since B and mu B is finite, so mu A is finite, mu B difference A is finite. I can take this to the left hand side, and then the claim is true. So using this claim, I can write mu of A and difference A as mu of A and minus mu of A. Now this limit is 0. Therefore, limit n going to infinity mu of A n This is equal to mu of A. But what was my A? A was intersection A. And this is what we wanted to prove.
Yes, sir.
So, quantum additivity, when given that the mu of x is finite, it is same as saying that whenever a decreasing sequence goes to empty set, the corresponding mu ends go to 0. Okay. So, any doubt till here? Yes. Anything you want to ask till now?
No, sir.
Okay. Now, just one last thing I want to discuss. That is the proof of density of rationals and irrationals in R. Because once you understand that, in that proof there is actually very nice technique of analysis that might be helpful throughout the course as well as in other areas of mathematics as well. So let me just write density of rationals and irrationals in R. So how to prove this? We are going to use a very crucial fact, something called as the LUV axiom. Does anyone know what is the LUV axiom?
Never heard.
Oh, you never heard. Okay. What it says is that if A is a subset of R, which is bounded, or particularly which is bounded above, then there is a real number such that for each x in A, x is less than or equal to alpha, and for every beta less than alpha, you can find an x in A such that x is bigger than beta. So the first thing, this one tells us that alpha is an upper bound. And the next thing, this tells us that no number less than alpha is an upper bound. Okay, and these together they tell us that alpha is the least upper bound. For the set A. And this alpha we usually denote it by supremum of A. With the other way around. So you must have seen this. Maybe you don't know the name, but you must have seen this axiom somewhere. Yes? Yeah, please respond. Otherwise, I will not know whether you are understanding it or not. Yeah, Prasandip, did you understand what I have written?
Yes, sir. I'm understanding it.
Okay, so is there a difficulty in understanding this?
Yeah, I'm attending in the mobile, sir, and it is difficulty to grab
Okay,
suddenly. So
okay. So, see, what I am saying is that if a set is bounded above, then you can always find a least upper one. That is called the LUV axiom of R. Okay. So,
yes,
okay, you can perhaps look at that for me, and then if you still have any doubts, you can contact me through mail or something. Okay. So, using this LUV axiom, first we are going to prove that the greatest integer function does exist. So, step one is existence of the greatest integer function. What does it mean? You take any real number, you can find an integer k. In fact, you can find a unique integer k such that k is less than or equal to x, but x is less than k plus 1. And how do you prove this? So, I might not give you the complete proof, just the idea of the proof. You can fill in the gaps. So, idea of the proof is that let us look at this set S. Look at all those k's in the integers which are less than or equal to. So the first question is S non-empty? Yeah. So what do you think? Is S empty or non-empty?
So non-empty.
Non-empty. Why?
Yes, sir.
Yes, but why?
I think Archimedean property.
Correct. Again, because of the Archimedean property, this is not empty. Particularly, if this is empty, if S is empty, then what it means is that for every k in Z, k is bigger than x. But that means for every n in Z, minus n is bigger than x, which is same as saying n is less than minus x. But this means n has an upper bound. N has an upper bound. That is again a contradiction to the Archimedean property. Okay. So therefore S is non-empty. Now since S is non-empty, S is non-empty, is S bounded above?
No, sir.
It is not bounded above? It is bounded above, right? Because by definition, every element in S is less than or equal to x.
But the element is belongs to integer.
Yeah, but they are all less than or equal to x.
Okay, okay, sir.
It is bounded above. So S is indeed bounded above, and therefore by the LUB axiom, there is some maybe alpha I will write alpha in R such that alpha is the least upper bound of S. So from here, so I'm not saying that this alpha is in S. I'm only saying that this alpha belongs to R. From here, what we want to do is we want to construct some integer such that x lies between k and k plus 1. So for that, what we'll do is let us look at alpha minus 1. Alpha minus 1 is not an upper bound. Not an upper bound for S. Right? And since it is not an upper bound for S, it means there is some k in S such that alpha is bigger than or equal to k and k is strictly bigger than alpha minus 1. And now we claim that x is less than k plus 1. So why okay, are these two statements clear? This one?
Yes, sir.
So if this is clear, then this is also clear, right? X is less than k plus 1, right? Because if not, if x is bigger than or equal to k plus 1, this implies k plus 1 is inside S, but then alpha is bigger than or equal to k plus 1 because alpha is the least upper bound, would imply that k is less than alpha minus 1. K is less than alpha minus 1, which I know is a. So therefore, this claim must be. and then we get the result, right? That k is less than or equal to x less than k plus 1. And as an exercise, you can check that this k is unique. Okay. Okay. So is this existence of the greatest integer function clear? Yes, please respond.
Yes, sir. Yes, sir.
Okay. So once we have this, now we can prove the density of rationals in R. So what it says is that given a less than b, we can find a rational number such that it lies between a and b. So again, let me give you the idea. Idea of the proof is that since a is less than b, we can find an n such that nb minus n is bigger than 1. Right? Can we do that? Yeah, Prasanji?
So what is NB into NA?
No, nb minus n.
Okay.
Yeah. So can I say this that nb minus n is bigger than 1 for some n? This is just the equivalence property, right? Prasanji, are you understanding what I am trying to say here?
By yes, sir. Because 1
Yeah,
by n, you can take 1 by n, and obviously you can find a natural number such that b minus a is greater than 1 by n.
correct. So, but yeah, that is also correct way of writing. But what I want to say is because b minus a is positive, n times b minus a becomes bigger than 1 after some n. So there is some n such that nb minus n is greater than. Now, once we have this, let us take k as the greatest integer of na. Right? So this symbol means greatest integer lesser than or equal to n. Okay. If this is true, then what we know? Na is less than or equal to na, and this is less than greatest integer na plus 1. That is the definition of the greatest integer of the greatest integer function of any number. So let us call this new number as m. So now my claim is that this nb, this is actually bigger than m. No, this nb is bigger than m. So if not, then what will happen? If not, then nb is also less than or equal to m, implies that this interval na and b, this is contained in the interval m minus 1 1, m minus 1 to m, right? Yes. Uppusame, do you agree?
Yes, sir.
Okay. And what about Prasanjit?
Yes, sir.
Okay. But this cannot happen, right? Because this has length greater than 1 and this has length equal to 1. So something which has more length cannot be in something which has less length. So this is a absurd thing. Okay. So this claim must be true that NB is bigger than M. So what I have, NA is less than M and this is less than NB. But this is same as saying A is less than M by N is less than B. And this proves the result. So we have found a rational number which is between A and B.
Yes, sir.
Okay. Now using this, it is very easy to prove the density of irrational sigma. So the third step is density of irrational sigma. So what we will do again, given A and B, given A less than B, we want to find an irrational between them. So consider A plus root 2 or maybe A minus root 2 and B minus root 2. So A minus root 2 is less than B minus root 2. This would imply that there is a rational number such that A minus root 2 is less than R is less than B minus root 2. Right?
Yes, sir.
Okay. But now we are done. Because if A minus root 2 is less than R and R is less than B minus root 2, then A is less than R plus root 2 and R plus root 2 is less than B. Now the only question is whether this is an irrational number.
Yes, sir. It is an irrational.
Because R is a rational, root 2 is an irrational number. So then addition cannot be rational. Something which is not rational is irrational. So, okay. So why did I discuss all this is because using similar technique, one can prove that the dyadic numbers are also dense in R. So between any two real numbers, you can find a dyadic number. And all those things are going to be helpful in your assignment 3 if you have gone through the questions. Okay. So, all right, let us stop here. Do you people have any other questions?
Thank you, sir.
Thank you, sir.
So, no questions.
Yes, sir. No, sir.
So, fine. Let us stop.
Thank you so much, sir.
Sagar, are there any questions on YouTube?
No, sir.
So, fine. Let us stop. So, I'm ending the broadcast as well.